Okay, it's a pleasure to be here. Please interrupt me. I'll try to make it a Blackboard talk and so that we can make interruptions. I was planning to give first an introduction to the gauge-gravity duality for those of you who haven't heard about it, and then perhaps talk about more current topics. Should I do the introduction or not? Yeah. Okay. So the gauge-gravity duality is a relationship between gravity in the interior of some space. So here we have a theory of gravity in the interior of some space. And this is supposed to be equal to a field theory or a theory that lives only on the boundary. So here there is nothing in the interior, and there is a theory that lives only here on the boundary of this space. Okay. Now the duality, and it's important for reasons we'll see later, is valid as a quantum mechanical statement. So we have a quantum mechanical theory on the boundary, and here we'll also have a quantum mechanical theory of gravity.
That's a pure gravity?
Yeah. Well, yeah. When I say a theory of gravity, here I'm going to mean it in a very generalized sense. So a theory of gravity is a theory where the metric is a dynamical variable, right? And in addition to the metric, we could have other fields. And in general, we will have other fields. And we might have strings. And in fact, the only way we know how to construct a theory of gravity is theories of strings. And those are the examples where we really know both sides always involve string theory on this side. So it will be gravity plus string theory. Yeah, so the observables of the field theory will be correlation functions of local operators. So this field theory, as we'll see in an example a bit later, could be like a statistical mechanics problem. And so we give 2 points, which are 2 points on the boundary, and we compute the correlation function of operators at these 2 points. So this is point x1, x2. Right? So these are the type of observables we can compute on the right side. On the left side, we'll compute observables which correspond to deforming the geometry or the behavior of the fields far away. So we could say the boundary geometry could be a perfect circle or a perfect sphere, or it could be deformed. If we do that of deforming the geometry, then here we'll also be computing so the tiniest deformation of the geometry creates a gravity wave that goes to the interior. And this gravity wave is felt here at the second point in some way. And then that correlation function will be equal to, let's say, the deformation in this gravity partition function. I'll try to define it later a little more precisely. But it will involve the computation of this 2-point function will involve the propagation of waves through this geometry. Okay. Yes, they are relevant. They will be relevant. So something very important is that all observables in a theory of quantum gravity are things we measured at infinity, right? So in a theory of quantum gravity, we cannot ask what is the curvature at this point, for example. That is not a good thing because in a theory of quantum gravity, we sum over many geometries. So we have theory of quantum gravity involves sum over geometries, right? With some action, let's say, which might be the Einstein action or something like this, some generalization of the Einstein action. And so when you fix a point in the interior, you cannot fix a point that is the same point in all the geometries, right? So, but here we're going to consider geometries which are asymptotically ADS or which end on this boundary, which have a fixed boundary, and so the points on the boundary are well defined. Those points are present in all the geometries.
So these boundary points, these are points at infinity in some way, or what?
In this vague statement, let me just say there are points at some boundary, but this boundary is really at infinity, and it's an asymptotic region. So we're always going to be asking about asymptotic statements. Okay, and we could be in Euclidean or Minkowski signature. So first, let me discuss this first in Euclidean signature, and then we'll go to Lorentzian signature. Now, before I give you a little more details, I'm going to say this in more detail later. But first, I like to make a general statement, which is that typically this theory will be a UN gauge theory or SUN gauge theory. And the coupling of this gravity theory, so the amount that measures how different from the classical limit it is, which is essentially the Newton constant, is going to be proportional to 1 over n squared. So in the large n limit, we'll have classical gravity. So I said that two sides are quantum, but here when the limit is, when n is very large, this side will be very quantum, but this side will become classical. Okay? Will be well approximated by classical. And I'll try to explain a little better what this means. Yeah, so the duality is in principle valid for non-supersymmetric theories, but the examples we know precisely are all supersymmetric or very close to supersymmetric. Yeah, we expect it to be true without supersymmetry, but it's harder to find examples. So because the reasons it's true seem to be very general. So this is one. So we need n much bigger than 1 if we want the bulk theory to be classical. And we also want, so this is on the boundary side. And we want a strong coupling, very strong coupling. So very strong coupling between the elementary excitations of this theory, and I'll say more precisely what this means in a second, in order to get an Einstein gravity theory. So when these two conditions are true, we expect that the theory in the bulk should be a theory that obeys Einstein's equations, perhaps with other fields. So we might have Einstein equations plus other fields. So that's in general. I think I'll try to answer this question because I now will show how to relay the computations on the two sides more precisely, and then perhaps you can ask this question again. So now I'm going to. So that was a preliminary statement of what the duality is. So the duality is always valid, but it reduces to simple Einstein theory under those two conditions. Okay. Now. Yes. In general, so if the second condition is not true, what we get here in general is a very stringy theory. It's a theory with all kinds of string excitations. And if the first condition is not true, well, we don't know what we get. So, okay. So now we are going to discuss the Euclidean version. And by Euclidean, I mean the signature of space. And so here, the bulk side will be hyperbolic space. Okay, so we have hyperbolic space. And on the boundary, yes, of any, in principle, any dimension. Yeah, let's say, just to be more precise, let's say it's 5-dimensional hyperbolic space. Okay. No. Well, the example I was going to give more, well, let's see. It could be any, what dimension do you like? 4? Let's see, 4 dimensions. Yeah, it could be 4-dimensional. The problem is that it could also be that the boundary is our space, and then in that case, it would be 5-dimensional. But yeah, so for different applications, you want this in different dimensions. And so that is one aspect of this. And so here in the boundary, in this case, you will have a 3D boundary system. Okay. And okay, so that will be our boundary theory. And well, of course, here we're talking about ordinary hyperbolic space, right? So if there is some coordinate, we can choose these coordinates. We call them Poincare coordinates. I think mathematicians call them horospherical coordinates, where we have here 3 spatial coordinates that are the same as the coordinates on the boundary. And then we have a 5th coordinate, which essentially goes into this bulk.
So that's going network given half space.
What?
So hyperbolic space is viewed as half space.
Yeah, yeah. So we can represent. So another picture we'll draw equivalent to that is, so here we have R3, and then we have the c direction going in, right? So this is the bulk, and the boundary is just the top part, right? So we'll have a statistical system living on the boundary. So we'll have a Euclidean field theory living on the boundary. We can view that as a system in statistical mechanics. Okay, so right. So what's a natural theory we can have in 3 dimensions? One more thing I wanted to say is this statistical system will be at the critical point. So will be it's in the continuum limit, and will be at a critical point, so it will be scale invariant. So an example could be the Wilson-Fisher fixed point, for example. That doesn't have a known gravity dual, but the Larsen limit of that has some version of gravity dual. But another popular system to consider is Chern-Simons gauge theories. So we could have a system whose action is a level k Chern-Simons theory, d3x trace of a dA plus. So the Chern-Simons action that Witten was talking about, this is a topological theory. It's too simple for the purposes I would want to use here. And so we typically need to add some matter, so some matter fields, let's say scalar and fermion fields, which are coupled to the gauge field of the Chern-Simons action. So terms of this form, plus perhaps other couplings. Okay. So there are Chern-Simons plus matter theories. So these theories are not topological. So the original Chern-Simons theory is topological, and you have all these simple things in terms of knots and so on. This is more like a dynamical theory, but it has the feature that it's classically scale invariant. So it's a theory that doesn't contain a dimension-full coupling. So you expect that at least classically you have scale invariance, and when you consider quantum corrections under quite general conditions, this will flow to a fixed point, a nearby fixed point. Or in supersymmetric.
You have to have a scale invariant theory because gravity is.
No, yeah. So the reason, okay. The symmetries of the field theory will translate into symmetries of the gravity solution. Here I assume for simplicity that the bulk was going to be the hyperbolic space, which has many symmetries. In particular, it has a symmetry under rescaling, taking x to lambda x and c to lambda c, right? This is a manifest symmetry of this metric. And the existence of this symmetry in hyperbolic space translates into the existence of scale invariance symmetry on the boundary theory. Okay? And yeah, you could also do that. So you can you compactify, and then you have the full conformal group, and so we call those conformal field theories. Now, yeah, this could be in the fundamental, for example, or it could be in the adjoint. Yeah, typically it will be in the adjoint, and we'll also have fermions also in the adjoint. So the examples which are simplest to analyze are examples where we have a lot of supersymmetry, and then we have these A's, and also we have phi's, which are scalars, and also fermions in the adjoint representation. Well, roughly. Yeah. The physicists know I'm lying slightly. Now, if you didn't have a this duality is supposed to hold for any system. So if you didn't have a conformal field theory, then what would happen is that your space would not be would not have this simple form. It would be more complicated. So there will be an extra function here, let's say W of C. So that will be the more general form of the space. Okay. So the idea is you view this as an action or as a measure in your statistical mechanics problem. So one thing you could do is, for example, compute the partition function, which would be the integral over all field configurations A and over all, well, these are all the field configurations. And then as a function of of a and phi, we write that action, and then this will give us a number. Okay. Now this is just a number, and the idea is that this number that we get here will, in the large n limit, be approximately the same as a number we would get by essentially computing the gravitational action. Right? By gravitational action, I mean just computing the volume of ADS. So we calculate. Yeah, let me be more precise. So the gravitational action is just the Einstein action. With negative cosmological constant, which I'm going to set to 1. So we have the usual Einstein term. So this is an integral over 4 space dimensions. We have the 4-dimensional metric and the curvature. When we evaluate this in hyperbolic space, we'll just get a number. The number is, and that number is supposed to be equal to this partition function. So that's the simplest thing. Now it's infinite. Yeah. So I'm going to get into that. So hyperbolic. So any calculation you do will be infinite. So that is the first rule. But that is true both of the gravity side and the field theory side. So any calculation you do in field theory is also going to be infinite. That partition function is also infinite, and so they match. So that's good. So this is the 0th order match. But the match is even better. So we wouldn't be talking about it if it was just the infinities that match. But it's a good thing the infinities match, because otherwise, the idea is that you can regulate these infinities and obtain finite answers. And these finite answers are the things that match. So let me just give you an example of how you regulate, just to make this more concrete, because you might think I'm being too abstract, and not really. So let's do this 3-dimensional hyperbolic space. And let's say we have a sphere, as we discussed. So we have an S3 on the boundary. So we can choose the metrics now, a different set of coordinates. Okay. So we take the volume of, this is the metric of S3, and this is the metric of hyperbolic space. No, yeah, so whenever we choose a set of coordinates, we'll make some symmetries manifest, such as the rotations on the sphere, but not all the symmetries of hyperbolic space. Yes. But in principle, this space has all the symmetries, right? It's just that the coordinates I've chosen do not make all the symmetries manifest. And now I'm going to compute the volume, or more precisely, we could be evaluating that action. And we have the integral d rho of sine hyperbolic rho to the cube power. Okay. And so we integrate between rho equal to 0 and then some rho max. Okay. And that will be some cutoff. And now, indeed, I'm breaking at this step, I'm really breaking the full scale invariance and some of the symmetries. I'm only preserving the rotational symmetry. And then when we evaluate this, so we'll find some divergent. So there will be, so let's imagine we expand this in powers of e to the rho for large rho. So there will be terms that go like e to the 3 rho cutoff. There will be terms that go like e to the rho cutoff. And then there is a finite term, right? Okay. And the idea is that you throw away these infinite terms, and you keep this finite term. This finite term is well defined. You can just compute it from this formula. These finite terms are what you compare in the field theory. So in the field theory, you will also have similar infinities. They have to do with the fact that if you do the partition function of the field theory, and you put some cutoff, let's say epsilon is a short distance cutoff, this partition function will have a divergence which is proportional to the volume of your space. And there could be a divergence proportional to the volume times the curvature of your space. These are all boundary volumes. This is the boundary metric. So this would be the volume element on the 3-sphere. This would be the curvature of the 3-sphere. This should not be confused with the terms in the gravitational action that I wrote before. So it should definitely not be confused with this action. Okay. And these two diversion terms are the same as essentially these two diversion terms that we found in the bulk. We throw them away. We don't care about those. They are not universal. They depend exactly on how we do this cutoff. So if we add the constant to rho c, they will be shifted. But this will not be shifted. And so this makes sense and can be computed. And in fact, in many of the supersymmetric examples, there are techniques for computing this partition function precisely in a way that one actually gets an actual number or an integral, some very well-defined number for any n and k and so on. One takes the Lorentzian limit, and one compares with gravity, and one finds agreement. Okay. So no needs to match. Yeah. We don't know how to match it. If we knew how to match it, it would be nice, but we don't know how to match it, how to match the cutoffs. But yeah, in general, quantum field theory is the limit of the finite things that remain after you remove the cutoff. So quantum field theory is always a limit. So that's true independent of this duality or any duality. Quantum field theory is a property. Anything we talk about quantum field theory has to do with the finite quantities that remain after you remove the cutoff. And here we are discussing one specific example of this number.
I think I understand that this 3 rho is a dimension, but what is the rho alone coming from?
With this one?
Yes.
Oh, here is just doing this integral, right? Well, if any of you knows what's the primitive of sine hyperbolic? Well, anyway, it's just simply doing the integral, and it will be, so I'm expanding this integral for large rho, so it will go like e to the 3 rho plus e to the rho plus e to the minus rho, right? There are all these terms in this cubed expansion. Here all I did is to expand the sign, and then I integrated each particular term, right? And the large rho contribution will come from these two terms, and yeah, it's totally trivial, no non-trivial statement here. Exactly, yeah. You get those things, and in some dimensions you get something that goes like rho c. It's related to the presence of logarithmic divergences in the 4-dimensional theory and so on. And so always the terms that are interesting are the finite or these logarithmic terms in any dimension. Depending on whether it's even or odd, you get finite terms or odd terms. This is an example of one quantity. This quantity is particularly interesting because one can compute, in supersymmetric theories, one can actually compute it in the field theory by some techniques of supersymmetric localization, etc. So you can, and to actually do the computation on the gravity side, you to actually compare with the computation, you need to compute this coefficient on the gravity side precisely. You need to know how the Newton constant that appears there is related to the parameters in the field theory. And from what I said so far, you could say, oh, I can always fix the parameters so that it works. But the relationship of the parameters was figured out before these computations were done, so it's not a circular argument. Okay, so that's one particular example.
So,
and
so the main
yeah.
formally invariant too. So
Yes.
how is this correspondence made?
Okay, yeah. So let me be a little more precise. So, so the way this works, if you want to actually do a full comparison, as I was mentioning, you need to say exactly what field theory we have. And so then we look at the simplest, so the simplest known field theory in 2+1 dimensions is, or a very simple example is a theory with n equal to 6 supersymmetry. So it's like the maximally supersymmetry. Well, it's not quite the maximum, but it's a theory with many supersymmetries, which is a Chern-Simons-like theory with 2 gauge groups and which have some Chern-Simons levels. Okay, so it's a theory of this kind with 2 Chern-Simons terms and so on. And the important thing you need to know is that it has 2 parameters, n and k. Okay, so everything is in terms of n and k. Okay, that's the field theory description. And now I'm going to give you what the gravity description is. So the gravity description is you start from an 11-dimensional supergravity theory on a space which is ADS4 times S7, okay? And then this S7, you take symmetry of the S7 that has no fixed points. There is a symmetry like this in S7, and you quotient that by set K, okay? So I hope this is clear. If not, I'll explain it later. And then you have n units of 4-form flux, F4, n units on ADS4. So, yeah, just a second. Yeah, what did you say? Exactly, yeah, yeah. That's what this CK is. Yeah, it's a unit sphere in C4, and it has the overall complex multiplication. Is that what this CK is? If you didn't understand what this is, it's just simply a specific space. So the important thing here is I'm talking about the specific space, and we also have a kind of electric type flux on the ADS4. It has 4 indices. And this obeys the equations of motion of 11-dimensional supergravity. And those equations of motion fix the radius of these two spaces, first relative to each other, and in overall units relative to the Planck, to the 11-dimensional Planck scale. And they give us a space, some ADS4 space. And after we are done with that, we can actually do this gravity computation we discussed here. We put it in the 11-dimensional action. We reduce first on the S7. We end up computing the volume of H4. This is the Euclidean version of this is just with H4. We compute the volume exactly the way we discussed, and we get a well-defined number. Many more. Yeah, we have all those fields, but all we are doing right now is computing this volume. So those fields are not excited. We have just this round 7-sphere quotiented like this. We have exactly this manifold. And we compute the volume or the action for this particular manifold, okay? And that's the thing we compare with the partition function, okay? It's just one number we're talking about. Okay? Now here I discussed one specific number. Well, maybe I probably should tell you a little more. I mean, once you, in this particular case, this number goes like e to the n to the 3/2 over times k to the 1/2. Okay, that's exactly how it goes, and then there is some specific number, and you can compare the two numbers. Okay. Now, the thing is that it's not just a number that we can compare, but we can compare functions. So now now this will come a little more non-trivial. This I wanted to keep. Well, anyway, you'll remember that. So let me define a slight generalization of this computation, where instead of taking a round sphere, we take a deformation of the round sphere. So we have some 3-dimensional space with a generic metric, right? So on the field theory side, we can compute the partition function with a generic boundary metric. So this is a 3-dimensional boundary metric, right? And this is the integral over all fields A and phi or whatever, e to the action for A and phi, and it depends on the boundary metric, but the boundary metric is not integrated. What's integrated in this sum are the fields that live on the boundary, right? So the boundary is a fixed background, and on this boundary we have a statistical mechanics problem of summing over all field configurations, right? Yeah. Simple version could be imagine an Ising model defined on the boundary, and we sum over all the Ising spin configurations, for example. Right? But the result will be something that will depend on this 3-dimensional boundary. So for S3, we'll get the number that we were discussing before. If we continuously deform the S3, we'll get a series of continuous numbers that represent this small deformation. Now, in the bulk gravity theory, this can be approximated by the following solution. So the idea is that this will be approximately equal to the same thing we had before. So it's the gravitational action evaluated on a classical solution. So this is a 4-dimensional metric now. This was a 3-dimensional metric, which will be a classical solution of the Einstein equations. So these are the Einstein equations for the action I have erased. So that's the action with negative cosmological constant. So this metric will obey the equation, the usual Einstein equations. Okay, so the metric, the Einstein equations with the cosmological constant, and with the following boundary condition. So with the condition that if we take the line element of this metric, this is in 4 dimensions, and we approach the boundary that is far away, then the metric near the boundary will have the form will have the following form. So C is the coordinate orthogonal to the boundary, right? And we can always choose coordinates so that the metric has that form. So C is a coordinate orthogonal to the boundary. This is the 3-dimensional metric that was our data. So that was the thing we are trying to compute. So we're trying to compute a function of this 3-dimensional metric. And this number will depend on this 3-dimensional metric through the boundary conditions for this problem. So we are solving a differential equation with boundary conditions and evaluating the action, and the value of the action for the solution of the equations will depend on that boundary metric. Right? And that's what we're doing here. Okay, and the gauge gravity duality relates this computation, says that it is approximately equal to this one in the large n limit. Okay, is that?
You have to go to the final limit to get that? Or?
Yeah, to get this, we need to go to the n goes to infinity, and k goes to infinity, and n over k is much bigger than 1. So I discussed those two conditions I discussed before. So n going to infinity is that condition that we needed always to have a classical theory. To have the Einstein theory, in addition, we need this condition, which for the actions of the kind we are considering here, that's the effective coupling of between the fields, because when you have these 5 fields, for example, they can exchange these gluons, and the couplings here of order 1 over square root of k for each factor. So a diagram like this will go like k times n, and well, that's the effective coupling. Well, if you didn't follow this, let's just say that this is the effective coupling, what measures the size of quantum corrections in the boundary theory. Yeah. So it just really saying that you have this ADS space, and when you conformally compactify, so if you can take this infinite space, you can multiply by a function. So let's say you have the 4-dimensional metric, and then you have you multiply by some function that vanishes at the boundary, right? In this case, you think of this as the function c squared. So I call it c squared, right? Times the metric, this original metric g. This is a metric which is finite, and the idea is that the geometry at the boundary, right, at c equal to 0 of this metric, all I'm doing is just rescaling this factor. It's just the actual geometry of the space, right? It's the geometry of the 3-dimensional space. So this problem is totally geometric. So you see, the original problem involved only the specification of a 3-dimensional geometry, and the idea is that doing this sum, so this sum is effectively done by looking at the 4-dimensional geometry that fills this in, right? You have this 3-dimensional geometry, you fill it in with a 4-dimensional geometry, and you solve the classical equation. So it has to obey there are an infinite number of geometries that can fill it in, but you pick the particular one that solves the Einstein equations. And no, this is not the moment you have a metric which is not the round sphere, right? you will break the symmetries, the global symmetry or global isometries of your space.
Yes, but I was only into the conformals.
Yes, yes, it breaks the it breaks the translation and conformal symmetries. But locally, you do have. So this is a space which locally has this symmetry. So if you go to some small neighborhood, you'll have approximately these symmetries. But yeah, indeed, globally, in general we will not have any symmetry. So, but that's yeah, this is fine, and this is also what happens in the field theory. Which, if you put a metric, which let's say, for example, let's do something simple, a metric which depends on position, right? It will break the translation symmetries of the problem. So, and it will also break the scale invariant symmetries, the scale symmetries. But it's fine. This is what we have, and for any conformal field theory, once we put external sources, we'll break the symmetry. But this breaking is completely controlled, and the underlying symmetry of the problem will imply that this function has to satisfy certain properties. So it has to be conformal. So this is the answer for this is a conformal invariant function of this metric G. So if we do a conformal transformation, we could do a conformal transformation G here, and then G will transform in some particular way. If G is fixed, then we'll break the symmetry. But if we transform G, we will get the same answer that we had before. And so that implies that this G and another G that differ by transformation give the same answer. So for example, let me give you a specific example. So suppose you fix a 3-metric G, and now you rescale the metric. You take the same space and you make it bigger, right? So the scale invariance of the theory tells you that this should be the same as lambda times 3GB for any lambda. And this lambda can even be a function of x. So for any lambda function of x, so naively what you expected from scale invariance is just that if you rescale lambda, you have even somehow this stronger symmetry. Well, yeah, it's a symmetry also of the field theory that even if you make local rescaling, you will get the same answer. Now, of course, the 3-dimensional metric depends on more variables. So this is one of the degrees of freedom in the metric, that there's more that you cannot rescale.
But what I mean is, if you do this at the metric of infinity, because you did not change the z in the same term, you get a different kind of integral for the verb.
Right. So here, for example, if you rescale, so how does it manage to give you the same answer, right? You're asking me, I think. So what would happen is, this is one problem, and the other problem will have a lambda here. They look different, but we could rescale the coordinate c, and then the metric will look identical. However, in the original problem, we were putting some cutoff. So the cutoff breaks this, but it breaks it in a controlled way, so that the only terms that end up depending on lambda are the ones that depend on the cutoff, and all the finite terms do not depend on lambda, right? So that's in detail how this works. So if you could ignore the cutoff, then you see that the two asymptotic boundary conditions are identical for the two metrics. And then I'm further saying that the cutoff doesn't break this in any way. Yeah. Okay. Now, so this was the classical version. And if we wanted the finite n version, so in principle, we will get here further corrections. So this is the leading classical approximation. And then we'll get extra terms that are of order 1 in n, and terms that go like 1 over n squared, etc. And these terms will arise by considering the functional integral over fields in the bulk. So in the bulk, we'll have the metric and maybe many other fields. So in that example we discussed there, we have the metric in 4 dimensions and the metric in 11 dimensions and so on. And we'll have to do the functional integral over all these fields around the vacuum. So we'll get a bunch of functional determinants, and that will be this order 1 contribution. Then we introduce nonlinearities in the action for those fields, and it gives us these terms and so on. Yeah.
So, but why is it well defined to integrate over these metrics in very high dimensions?
Yeah, this is a very good question, and because it is not, so it is not well defined to do this integral. These determinants are infinite, and this is an infinity which is different from this volume factor. It's an intensive infinity, right? First, there might be an infinity due to the, and those are really finite once you compute them in string theory. So for that, you really need to go to string theory, and when you compute them in string theory, you'll get finite answers for these quantities.
So is there anything like a systematic one-over-n expansion?
In a string context, yes, there is. So that's so string theory provides a systematic way of doing this expansion in such a way that each term will always be finite. And that's in fact one of the nice things about string theory, that it gives you the possibility of obtaining finite terms for all of this. So conceptually, in the long distance limit, you get a piece which is the determinants, and all divergences get replaced by computable coefficients in string theory. And there are some specialized tricks to try to compute them in these specific cases. But the conceptual idea is that string theory provides the way to compute all these determinants and so on without the short distance divergences in the bulk. Okay. UN?
So if you use SPN.
SPN, yeah. So yeah, you get for other groups. So typically, when you do SPN, you get non-oriented strings, or you get these things called orientifolds in the bulk. And yeah. So, but it's well understood how to understand this case. Other case. Yes.
Maybe it's because you look
Yeah.
at this four-dimensional example.
Yes. Yes.
But what is string theory in 11 dimensions?
Okay, I also again oversimplified. So if you really wanted to do this in a string theory context, what you would need to do first is to take k, which is relatively big. So you will need to take this type of limit. First, you take n to infinity, k to infinity with this fixed. Okay, and there what you get is you get 10d string theory on ADS4 times CP3. Okay, so if you take S7 and you remove completely the circle, you get CP3. That's like the CPN example Nati was talking about. If you remove the phase completely, you get this. And now you would have to do the string theory computation on this background. For the sake of full disclosure, this hasn't been done. So it has not, this full string theory, like the corrections there. This order 1 correction was done somewhat indirectly, but these other corrections have not been done. But in flat space, those corrections can be done, and they give you finite answers. In these cases, they haven't been done, but they're expected to give finite answers for the same reason that they give finite answers in flat space. Okay. Yeah.
So this kind of
No.
perturbation theory, is that the one where you do perturbation in the genus? Or
In the genus, yeah. So this is the genus expansion in string theory. So this would be like the genus 0. This is the genus 1. And this is genus 2, and so on. Now, in these backgrounds, already the genus 0 is tricky. So there is something quite interesting, and there was a lot of work invested in understanding this genus 0.
do you have a hyperbolic background?
Yeah, not because of not in the partition function case, but when you have excitations. There is an interesting transmutation of excitations between the ones you have at weak coupling and the ones you have at strong coupling. Yeah, I'm not sure whether to discuss this in detail now, but it's actually lots of fun mathematics with integrability and so on that go into this to go between the weak and strong Toft coupling. So I said that we keep this fixed. If these were very small, it's trivial to calculate these anomalous dimensions of operators. But if lambda is large, it's more non-trivial to calculate them from the original theory. And they give a nice matching. So I could speak 5 minutes on that if, well, maybe I'll skip this. Skip that. Yeah, maybe, yeah, I will talk about something which perhaps I'm sure at least some of you know a lot about, and perhaps so which is matrix models. And I'll try to relate this duality to something you know about matrix models, and try to show you how it is similar to things you do in matrix models, and also how it is different. Okay. So here I'm going to start talking about the standard matrix integral, so the Gaussian matrix integral that I guess you probably all know. So this probably will touch base with something at least some of you know very well. So we imagine you are doing a matrix integral over n by n matrices, call them M, e to the minus 1 over some g squared trace of m squared. Okay. M is Hermitian. Okay. And so you all know how to do these integrals. So you're supposed to first you write m equal to u m1 up to mn. You diagonalize m, and you end up with an integral over the eigenvalues, dmi. So these are only n variables of simple action, which involves the van der Monde determinant and a sum over all the mi's squared, right? And then this integral is done by looking at the eigenvalue distribution. So you look at the eigenvalue distribution, you introduce a row of m, where m is the eigenvalue. And this eigenvalue distribution has the shape of a semicircle, some constant, minus m squared, right? Which looks like that, right? I think there is even a poster outside these walls. Yeah. What? Yeah, this is in the large n limit. Yeah, so so this is all exact. And then at this stage where we replace this integral and use this eigenvalue distribution, then let me say the following way. So we view this as some integral roughly over all the eigenvalue distributions of some function which now looks like e to the minus n squared, and the action is minus. So there is a term that goes like the integral of m squared. Let me put the minus here. And then there is a term that contains two integrals over m and m prime. Rho of m prime that comes from the van der Monde determinant, right? Log of m minus m prime. Okay, so hopefully this is familiar to everyone. And the saddle point of this action is this eigenvalue distribution. That's one way of deriving it. And notice that the original action in the regime we are interested in is not well approximated by saddle point. So this original action for each mi is not well approximated by saddle point. So the fluctuations of each mi are larger than this g. But if you bunch many of these mi together, then we have a well-defined eigenvalue distribution. And we can even write down this kind of action for rho, which if you look at the classical solution and you insert it here, will give you the actual value of this integral, or correlation functions and so on. So if you wanted to calculate a correlation function, you put in this eigenvalue distribution. You compute it in terms of this eigenvalue distribution. Okay, so this is something that you all know well. And
g was going to 0 in your limit?
yeah, so this is in the limit that g squared n is fixed.
So then wasn't the fluctuation of each mi also?
No, the fluctuation of it, well, let's compute it. So g is going to 0, but n is going to infinity fast. And notice that the fluctuation of each mi would be of order g with that action, right? But the distance between successive eigenvalues is of order 1 over n, right? And this is of order square root of 1 over n, right? So this is much bigger than this.
Right? Small compared to 1.
Yeah, it's compared. So we have lots of eigenvalues, and the fluctuation of each one is large compared to the distance to the next eigenvalue. So it's not correct to think that we have all these eigenvalues fixed at specific positions. They're all fluctuating. The density is very well defined. Yeah. So, yeah.
With this idea of trying to integrate over eigenvalue densities, is it it possible to reproduce the next correction to saddle point? I mean, of course, it's possible to do it.
Yeah, yeah. I think if you just do this, I think you do reproducing. I think you even reproduce it in one of your papers, but you have to worry about measure factors. Oh, maybe that's what you wanted me to say.
The saddle points without the cuts, and about
Yes.
those, it's easy to reproduce.
Ah, okay, yeah, you're right. Yeah, with the cuts, yeah, it's not clear. Yeah, and you have to worry about possible measure factors. So the content of this is what I wanted to emphasize here is the following. I wanted to emphasize that we have this problem in the Lorentzian limit. It naively is not classical in the sense that we cannot do this integral by direct saddle point approximation for these MIs. But what we can do is we can introduce this eigenvalue density, and we have a nice saddle point for the eigenvalue density. And so you should think in terms of the analogy that the original matrix is like the original Lagrangian that we had. The eigenvalue density is similar to the shape of the geometry, the shape of the bulk geometry. Okay? And in fact, notice that we started with an integral over only variables that live at a point, right? And we ended up here with something that depends on functions of one variable. So in some sense, we got an extra dimension. So we got this extra dimension, which was, let's say, this direction, the eigenvalue direction. And now we have fields in one dimension, right? So we started with fields at the point, if you wish, and now we have fields at one dimension. And at the level of this action, we just have a single field. And n is only appearing as an overall coupling, as the overall, let's say, Planck constant in this action. So when n is large, this becomes very classical. And then corrections to the Lorentzian limit is doing the quantum mechanics of this row. And as Shiraz was saying, well, it depends on, they might depend on measure factors and so on. Okay, very good. Well, I think I'm almost, well, there is one more. Okay, this is the analogy. And in this case, we have the possibility of doing the explicit translation between, let's say, these original matrix variables and this field, or this eigenvalue density. We understand it in great detail. We don't have a similar understanding for how to go from the original fields to the metric. So understanding that would be a derivation of the duality. So you would be able to start from the original fields, do some transformation, and then you end up with the metric and all the other fields. Okay. What?
Do you expect that it will always be possible to do this duality? Any reasonable field theory on the boundary?
Well, I think, well, let's see. I hope, I probably think, that let's start with the most speculative statement. I think it is possible to do it with any reasonable or unreasonable or any system on the boundary, right? So, but then we get something in the gravity which we don't know what it is. Now, in order to get the classical gravity theory, you need to start with a large n system. So a UN gauge theory or something of this kind. And in those cases, you expect to get some kind of string theory. Or M theory, as we saw in that case. It's not always a string theory. So in this case, we can also do this duality when k is 1, let's say, where we have ADS 4 times S7. That's on a particular example. In that case, it doesn't have a simple string theory. We only get this M theory description. But we expect to get some system that becomes classical. That's a theory that is becoming classical when n is large. So that's what is expected in general. And in some cases, it could be a weird theory, like a theory which contains gravity plus a bunch of other higher spin particles. So gravity is the theory of massless spin 2 particles, but we could have a theory with also massless spin 4, spin 6, etc. particles. And those are weirder theories, and we could get those. And we do get those when we have the weak coupling limit. So if this theory is very weakly coupled, then we expect to get such theories. So that the condition that I discussed before, that I said that we need strong coupling, I discussed in the very beginning a statement that I said we want strong coupling. That's to remove those weird examples, to remove the higher spin examples. And
but you always need the conformal theory on the
No, 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 no. Any theory, any question.
So, for example, let's suppose we take matrix phi to the fourth large n a la
Yeah.
the top.
Yes, yes.
Can
This.
one argue what the
Yeah,
argue-
yeah. So the dual should be some kind of string theory, and it will not be that scale. That theory is not scale invariant, and the dual will not be ADS, but it will be some other space which is not ADS, and we don't know what it is. So the question is I mean, if you ask me whether I expect it to be true, I expect it to be true, but I don't know what the other side is. So the example. So it's only in a few cases where we have concrete examples. I mean, this is an infinite sequence of examples we have. I mean, you can, for example, let me just give you a flavor of the example. So here you can replace this by toric. So S7 is the same as the cone over R8, right? And you can replace this by toric manifolds, toric Calabi-Yau manifolds, and you understand how to essentially find the corresponding theories. So these are, fairly general examples, but they're not the most general because those theories are still special. There.
So, is this correspondence understood by examples? In other words,
Yes,
you check
yes.
both sides,
Yes.
and you see that they correspond.
Well,
or is there
yes.
Is there a line between them?
There is nothing similar to what we have here, right? So here in the matrix model example, we have a derivation, right? We have nothing close to this, okay? What we have is there is one specific example where we can relate many things. That's this example I mentioned here, and also ADS5 times S5. There we can do
So
highly
it's not
non-trivial.
by just checking both sides without finding the direct link between them, is that correct?
Yeah, sorry. How did we know? I think maybe what we're asking is why did you expect from the very beginning that these two were related? Yeah, and that comes from some reasoning using string theory that you think of. So these relationships were first understood by thinking about branes in string theory. So you take a brane or a membrane. So let's say you take a membrane that has 2 + 1 dimensional, so like 3-dimensional, and it's embedded in, let's say, some ambient space, let's say 11-dimensional space. And when you look at the near horizon region of this membrane, you know both. From some string theory technique called D-branes, we know what the low energy dynamics is of these theories, and it turns out that it is this Lagrangian that we wrote here. And we also know that these are gravitating objects in the ambient space, and so they curve the geometry. So far away we have R11, and then close to these branes we have ADS4 times S7. Okay. So the S7 are the transverse dimensions to these branes, the transverse sphere to these branes. And so the idea is that when you consider low energy excitations on this space, you can reach low energy excitations in two possible ways. One is to have a very long wavelength excitation, which will have a hard time going into this brane. So those we're not interested in. And the other is to have a short wavelength, any wavelength excitation, but that is deep inside this throat. So this throat has a gravitational potential, which is essentially the metric of ADS that we've written here. So something with very large C will have a very small proper energy. So it will be redshifted to very low energies. So take something of fixed energy, move it down this throat, it will have very low energies. And so the idea is that this field theory describes everything that is happening deep inside the throat. Okay? And that was the original derivation. And this gives you a mechanism for generating new examples. So you find some D-brane configuration in string theory near perhaps some singularities, and you understand both sides. And that's one way to get examples. Or you can guess them from the symmetry. I mean, you can. It involves some kind of guesswork, either this type of derivation or some guesswork relating it to another known example. Yeah. Yeah.
Still for this duality.
Yes. Yes. Yes.
Speak of this 5. We have a well-established set of equations
Yes.
which relates one side of duality to
Yes.
the
Yes.
other by
Yes.
means of
Exactly. Yeah. 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 This is the topic I didn't. Yeah. Let me say a few words about this topic because. Yeah. Well. Yeah. So let me discuss in more detail. Let's say we keep with this example we were discussing, and we take this n going to infinity and k going to infinity, and keep n over k fixed. Let's call this lambda, some kind of coupling, and we keep it fixed, right? Now, if we go to the Lorentzian version of this theory, so we'll have now ADS4, and we can look at the energies of various excitations that we have in the interior, right? And similarly, in the quantum field theory problem, we can look at the anomalous dimensions of operators. So we can take some operator like, let's say, the stress tensor, right? This corresponds to, in the bulk, to a graviton, which has 0 mass, okay? And then the anomalous dimension of the stress tensor, which is 0, right? That's exactly for any CFT, no matter whether it's at weak or strong coupling, translates into the statement that the graviton has always 0 mass, okay? If we had some other operator which had some anomalous dimensions, then the anomalous dimension would be related to the mass of the particle in units of the radius of ADS, okay? And these could be non-trivial functions of the coupling. And what Volodya-Kazakov was referring to is that we have a series of equations that he and others derived to actually compute how this depends on lambda, okay? And what is found, what those equations show, is the following. So first of all, before we had these equations, we already had some expectations for what should happen with these anomalous dimensions. So when we are at weak coupling, so this weak coupling regime corresponds to the regime which can easily analyze in the field theory, right? And so here we expected that they grow sort of linearly. That's the first order in the coupling, and then we'll have further orders. So small lambda, that's field theory, and large lambda, we knew from the string theory side what the energies of these strings were, and we knew that they behave like lambda to the 1/4. Okay, this is for very large lambda. So very large lambda is the case where Einstein gravity is well defined and string theory is easy to analyze. This is the regime where we have weakly coupled field theory, and this regime in between is a regime which is hard to analyze directly from either of the two sides. And well, through the work of many people, including Volodya here, equations were found that allow us to interpolate between these two with a curve in such a way that it matches weak and strong coupling, and it certainly matched the previous predictions and so on.
It's not related to these integrable spin changes?
Yes, yes. These techniques, yeah, well, I mean, people who contributed to this were Weissert, for example, and developed many things in this area. And these equations, yeah. So Weissert and Staudacher and Eden derived an equation like this, but for something called the cusp anomalous dimension. And then in their paper, the paper of Volodya and company, they derived it for general operators. But yeah, so it's and there's a lot of interesting mathematics related to integrable systems behind this equation. So this is one of the very mathematical areas of string theory and even of this gauge gravity. You compute the full curve, and this curve is obtained as, I mean, this you should get Volodya to give you a seminar. But this curve is computed by solving a set of integral equations, similar to the thermodynamic Bethe-Ansatz equations of integrable systems. And solve those equations, you get this curve. So if you wish, this is a check or a very strong test of the gauge gravity duality. You find that the two regimes, which look different, are connected, and that's what the original statement was. But not only that, it allows, I mean, these functions allow you to compute non-trivial anomalous dimensions in 3- and 4-dimensional interacting theories, exactly, which is something that wasn't possible to do before. So, like for example, for the Ising model, you could compute the dimensions in epsilon expansion and so on, and that's an approximate expression. So these are formulas which give you exact anomalous dimensions in an interacting theory in 3D, for example, these Chern-Simons matter theories. So this could be like toy models for other systems, in the same way that the Ising is a toy model for strongly interacting for condensed matter systems. This could be also toy models for condensed matter. In general, they are a bit unrelated. Well, when they are used for condensed matter, you have to take into account that n here is infinite. So it's like an infinite n analog of some system you might be interested in condensed matter. In the same way that when you have an ON model.
Is there any 1 upon n expansion?
Yeah. So the 1 over n is the string loop expansion. Yeah.
Genus expansion.
Yeah.
But I mean, can you get x models that way too? Or?
Yeah, so this delta that was computed, that's the leading order in n. So what they computed was delta, that's the leading order in n, and then there will be the 1 over n squared times other function of n. Delta is the function they computed, right? F0, genus 0. And then there is a genus 1 function, and this hasn't been computed, and it's not known how to compute it. I mean, it's a harder problem. So now it's the effort in this area is mostly in computing other quantities which are more complicated than anomalous dimensions, like correlation functions and scattering amplitudes. And there's been some progress in scattering amplitudes. Well, I'm out of time, but if you, there is one thing that I think I should mention. Maybe I'll mention it briefly. And it's the fact that when you go to the Lorentzian picture, part of what I'm going to say is already included in this Euclidean picture, but when you go to Lorentzian picture, one interesting thing you could try to consider is you can have the boundary, and in the interior you can put a black hole. And this is related to a thermal configuration in the boundary theory. Right? So we considered exactly the same theory we had before, and we think of the boundary as S2 times time, right? Now we're in Lorentzian signature, right? We have the S2 far away, and we have a black hole in anti-de Sitter 4 space, so 4-dimensional anti-de Sitter space. And the idea is that this black hole corresponds to a thermal configuration in the boundary theory, some kind of gas or plasma of particles in the boundary theory. And small perturbations of the black hole that have long distance expansion. So if you replace this by R2, for example, you can consider long distance expansion of long waves on these black holes or black brains, and they correspond to the hydrodynamics of these theories. And that also has been derived. You can relate Einstein's equations to hydrodynamics, and this is something that Shiraz and company, and Mukund, who's sitting there, and Veronica, who are also sitting there.
What kind of hydrodynamics?
Just you can derive the ordinary Navier-Stokes equations in some limits. So, but first you derive relativistic versions of these equations, and then you can take the further non-relativistic limit, and you just derive the ordinary Navier-Stokes equation. So, so in this setup,
Is the equation any better behaved or any worse behaved?
no, they are equally. These are mathematical equivalent. So anything that, but Einstein's equations are more complicated than Navier-Stokes equations. So if you try to win the Clay medal by solving, it doesn't look like a promising approach. So maybe someone could try it. Maybe the Einstein equations are secretly nicer. I don't know. Yeah. So yeah. So I think I will end with this, and unless you have some other questions.